Are there questions on what we've been doing so far? Yeah.
There was one thing. So I was thinking of, so with the CSS codes, it makes sense when you look at the number of generators that the k is k2 minus k, or plus k1 minus n. But for a code that's perpendicular to another code, if the first code's k has k, and the second one's k will be n minus k, the first one. So when you sort of, so I substituted those, or sorry, thinking of the Hamming bound example where we have like a 7.4 code and a 7.3 code that we use to make the 7.1 code, 4 minus 3, or 4 plus 3 minus 7 would be a 0.
Right. So there, we're not using a 7.4 code and a 7.3 code. We're using two 7.4 codes. Right? So we're using, so that the Hamming code is weakly self-dual. So it's included in its dual, but the dual has one more vector, basis vector. Okay? And, or sorry, one less basis vector. So one of those ways around, whichever way works. The point is we're using the one that's bigger. And so you only get 3 parity checks for each of them. Right? So if you remember the stabilizer that I wrote down, there were 3 x1s and 3 z1s. And so that's why you still have one left. So you're not using exactly the orthogonal ones. You're using something that's a subset. Okay. Other questions? Okay. So I have a couple of different things I want to do today. So I was going to start out by talking about how we generalize stabilizer codes to QDITs. So QDIT is going to be, instead of a dimension 2 Hilbert space, a dimension D Hilbert space. And the first thing we want to do, we need to do if we want to make a generalization of stabilizer codes, is to generalize the Pauli group. So so the Pauli group is going to consist of things omega to the a, x to the b, z to the c. Sorry, the Pauli group for one thing, for one QDIT, and Pn is tensor products of this. And so then what are these things? Well, omega is just a d root of unity. So, well, let me get back to that in a second. And then x is the analog of the bit flip, which is going to be the operator that adds 1 mod d. And z is the analog of here, maybe let's call these I. Or J even is better. And Z is the analog of the phase flip. And so what it does is omega to the power J. So you can certainly see in the case of D equals 2 that this specializes to the regular Pauli group. Well, no, let me say that. This specializes to X and to Z. But it's actually not exactly the regular Pauli group, right? Because when D is equal to 2, omega is minus 1. And so you're only getting phases plus or minus 1 here, instead of plus or minus I and plus or minus 1. And the reason for that, I mean, so you could develop a theory of stabilizers that just had this plus or minus 1 here, and it would look basically the same. But it causes problems later on. In particular, it causes problems when we get to the Clifford group, which hopefully we will by the end of today. And the underlying reason is that there's kind of something fundamentally different about qubits and odd dimensional qubits, which gives you these extra factors of I popping up somewhere in the theory of stabilizers for qubits, but they don't show up for odd dimension. And so mostly we're going to focus on the case with d equals prime, and you have to think separately kind of about the odd prime case and 2. So 2, of course, is the oddest prime of all, being even. Anyway, so this is what we're going to use for the Pauli group in kind of the general case. So the multiplication rule for these, of course, you can work it out just from these operator definitions, but it's helpful to write it down. And this is omega to the BC minus AD. This is a commutation rule, I should say. So here you see the generalization of this property for qubits, where things would either commute or anti-commute. In this case, if you try to commute 2 Paulis past each other, you get some power of omega, the d-iterative unity. And the specific power you get is BC minus AD, which you can recognize as kind of a symplectic inner product again. And this time it really does have the minus sign, right? Because if you're taking mod d, well, minus 1 is equal to d minus 1, but it's really different from plus 1. Okay, so so from now on, I'm going to specialize to d equals p of prime, an odd prime. Okay. And so once we have this Pauli group, we can go ahead and define stabilizer codes in pretty much the same way. So given subspace Q of n qubits, so it's going to be, I guess, H sub p tensor n. This is the subspace of that. You can let the stabilizer be the set of Paulis that fix every code word. And and then analogously, if S is an abelian subgroup of the Pauli group, and omega I is not in S, then we can let T of S be the set of psi such that m psi is equal to psi for all m in S. So you see that definition is just the same. The only difference being that I'm requiring now that it's omega that's not in S rather than minus 1, which is really the same thing, right? Because omega is the generalization of minus 1. And then we can also let n of S, again, be just the things that commute with it. So Okay? So you see these definitions are just the same as for qubits with that one small change. Yeah, so what else do you need to know? So the weight is still the number of non-trivial tensor factors. Of an operator. And so you can use that to define distance for a general QDIT code as well. And if you have a non-stabilizer QDIT error-corrected code with n physical QDITs, logical Hilbert space, of dimension k, big K, and distance d. We say it is, so we use the same double parentheses notation, and now we just put a subscript indicating the dimension. And then a stabilizer code that has big K is equal to, d to the little k is a double brackets n k d sub d code. Okay? So these two things are just notation. So it's all completely analogous, and you just put the subscript to indicate the dimension. Okay? And so more stuff that's the same. But for this, well, okay, let me just state it. So if S has R generators, then the code space T of S encodes n minus R logical qubits. So this is something that actually fails when D is not prime. And the reason for that is when D is prime, then kind of all the generators are going to have order D. Everything in the poly group will have order D, basically. But when D is not prime, then you'll have some things that have order that's a factor of D. Right? So for instance, if D is 6, you can have things of order 2 and order 3 and order 6. And so it matters how you choose your generators. First of all, it matters because if they have these lower orders, then the size of the stabilizer will be smaller, and you'll kind of be ruling out fewer states. But it's also possible, even if you're choosing the generators to have maximal order, that you can get products of them. Well, you always will have products of them that have less order, but you can have kind of more interesting options for what those products are. Okay. And then the second property is I think also true if G is not prime, but And that's the property of the distance. And so the distance is given by the minimum weight operator in n of s minus s again. Yeah.
So what was by order? What did you mean by order in the previous?
Oh, yeah. Sorry. If you take a Pauli to, so for qubits, if you took a Pauli to the second power, if you square it, you got the identity, or it's minus the identity if you had the phase I. And so we say those things have order 2, because if you take them to second power, you get back to the identity. The order is the lowest power that you raise something to and get the identity. So for d equals 3, everything will have order 3, meaning if you cube it, then you get back the identity. So if you look at like x over there, x cubed is going to add 3 mod 3, which is just doing nothing. So it's the identity. And similarly, z cubed will take you to the power omega to the j, but omega is a cube root of unity, so raising it to the third power gives you 1, and it doesn't do anything. Okay, but no lower power will have that property. Whereas if d is equal to 6, as in my example, then you have, say, a 6th root of unity. And if you look at z cubed, then and then raise, so that's a different Pauli, right? That's a valid Pauli. It's not the identity. But then if you square that again, then you are getting the identity, right? So z cubed has order 2. Yeah.
I'm trying to wrap my head a bit around the normalizer. So with the stabilizers, our logical errors were equal in size to the normalizer of S, not including the stabilizer. If that were to continue with like Q dits, then like for example if we had like 3 states, then we would have 2 logical x's, 2 logical z's, 2 logical y's. We have 6 operators, but there's no 3 to an exponent that gives me 6. So I feel like I'm
right. Yeah. So yeah. So first of all, there's not a clear analog of y anymore for qubits. So remember, what's in the Pauli group is, ignoring phases, it's x to the b, z to the c. Okay. So for q bits, y was x times z. Right? But now b and c, remember, can be, it's maybe even worth writing this down. So a, b, and c can be anywhere in the interval. Well, they're sorry, they're integers. So they can be from 0 through d minus 1. Okay. So you do have x times z. That's a valid thing in the Pauli group. We also have x squared times z and xz squared. And if d is larger, then you have x cubed, z squared, and so on. And in fact, yeah, an x squared, z squared is in there as well. So that's what you're missing. So the logical Pauli group is also going to have all of these things. And the size of the Pauli group, ignoring phases, is d squared. With phases, it's d cubed for one qubit. Okay? Other questions? Yeah, and so again, it's also true. I mean, if you want to have some weirder group of errors that you're correcting, it's again true that the stabilizer code can correct that set of Pauli errors if and only if the product, so E dagger F is outside n of s minus s for all pairs. And I could say that in this case, for qubits, E dagger is actually different from E, right? For qubits, the Paulis were Hermitian, so the dagger didn't really do anything. But in this case, it does. It basically is taking the minus of the power, right? So x dagger is not adding 1 mod d, it's subtracting 1 mod d, for instance. Okay, and elements of the stabilizer are of the form so there are so if you have the generators if the generators are M1 through MR, then the general element is going to be the product of I equals 1 to R, Mi to some power Ai, where Ai is between 0 and d minus 1. In this case is P. But again, this is specializing to the case where d equals prime, because, again, otherwise you have possibility of weirder stuff going on. Okay? So let's look at a couple of examples. So the first one is going to be a very simple example. So I'm gonna work with p equals 3, so q crits, and we're gonna have n equals 3, and then there's just going to be 2 generators for the stabilizer, xxx and zzz. Okay. So the first thing to notice is that these things actually commute. For q bits, remember, they wouldn't commute, right? Because we'd get 3 minus 1s. But for q crits, they do commute, because we get a factor of omega each time we move an x past a z. And omega is the cube root of unity. So omega cubed is 1. So this code, it has 3 qubits, and it has 2 generators. P is prime, so it has 1 logical qubit, 1 logical q crit. And then what's its distance? Well, we can see that if we have any weight 1 Pauli, it's going to be something of the form x to the a, x to the b, z to the c. And the x part will not commute with this thing. The z part will not commute with this thing. So any weight 1 Pauli will not anti-commute, will omega commute to some power of omega with one of these, at least one of these 2 operators. Okay? So there's no distance 1 things in n of s at all. But there are weight 2 things, right? Because if you look at, say, x tensor x inverse, right, that commutes with this, certainly. And it also commutes with this, because we get 1 factor of omega and 1 factor of minus omega. Oh, sorry, omega inverse, I should say. Okay? So that means that this is a distance 2 code. Now, I should say that for the case of qubits, we don't have any such code, 312 code. We do have a 422 code, which looks similar. But you can prove that there's no 312 qubit code. And so this is an example of why it might be worthwhile to go to higher dimensions, right? Because you can make, you have more options, you can make a smaller code. And I should say this is not something that's just about stabilizer codes. It's actually true of any quantum arc reckoning code for qubits versus q crits. Okay, so why would you care about a distance 2 code? Well, it's not as interesting. But distance 2 code, remember, are still useful for correcting erasure errors. And they're also useful for detecting errors, even if you don't want to correct them. Okay. So are there questions so far? Yeah.
So the same definition of distance applies in the qubit.
Yeah. So right. So the distance. Remember the definition of distance for general quantum error correcting code made use of the notion of weight, right? But other than that, it didn't really depend on having qubits versus qubits. Right? You needed some kind of tensor factorization in order to define weight. But once you do that, the distance is just kind of the minimum weight thing that doesn't satisfy the quantum error correction conditions.
And the results that follow through also carry on. In terms of like the number of erasure errors incorrect and number of
Yeah. Those nowhere that did they make use of the notion of qubit except in the definition of weight. Yeah.
A question then about weight, because then like if X sort of cycles through all your possible states, if you get a lot of states, like you have 15 different possible states, X7 seems like it's further away or than getting back home than like X14. Sure. So shouldn't it have less or greater weight?
Yeah, so I mean, in the usual definition of weight, it doesn't matter. But you're right that when D is large, it seems maybe wrong to say that X to the first power is the same as X to the seventh power. So what you want to do there is define a new notion that kind of captures what you like. And then maybe is when it makes sense to not talk about the distance of the code, because again, that's using the weight, but just to say, well, here's a set of errors that I want to correct. I want to correct, X to the first power, X to the second power, but I don't care about X to the higher powers. And in fact, you can come up with codes that will do this. It turns out this is a case where you actually don't want to look at prime dimension. But yes, it's a very sensible thing to do. Okay. Okay. So the next example is going to be a qubit analog of something that does exist for qubits, which is the 5-qubit code. So here's a stabilizer. Okay, and so this you can work out is a 513 qubit code. Okay, and it's a perfect generalization of the qubit case. It's just that these inverses for the qubit case don't matter, right? They just give us back x's and z's. Okay. So this is just to give you a flavor of the types of codes that exist for qubits. Okay. So let's see, which order should I do this in? Okay. So one more example. So this is a family of codes that's a fairly interesting family, which is called the polynomial codes. So polynomial codes are related to the classical Reed-Solomon codes, if you know something about classical error correction theory. And it's actually, so these are CSS codes. I guess I didn't define CSS codes yet for qubits, but it's straightforward. And but it turns out to be a bit easier to define them using the kind of standard basis encoding. but they are stabilizer codes. And so these polynomial codes are defined this way. So what we're going to do is we're going to let alpha 0 through alpha n minus 1 be distinct non-zero numbers in Z mod P. So this is already saying that P has to be greater than n. But other than that, it's going to work for all P. And then given these things, we're going to encode this basis state labeled by K mod P numbers to be a sum. So F is, yeah, okay. So F is going to be a polynomial. And then we evaluate this polynomial on these n different points. Okay, and we're going to sum over different polynomials. So F is a polynomial of degree less than or equal to g. Such that So we can write such a polynomial this way. And we're going to insist that Cj is equal to Aj for j less than k. Okay? So we're taking a polynomial of degree at most g, and we're saying the first k coefficients of it are given by this index of the basis. Okay? And then we're going to sum over all the higher coefficients, including zeros. Right? So it can be degree less than g. And then each such polynomial is going to give us a term in a superposition. Okay? So you see this has kind of the same form as the CSS codes we talked about before, right? It's a sum of different basis states. So these are, like I said, are related to the Reed-Solomon codes, these basis states. But there's some constraint, which is like being in this C2 perp. You had a question? Okay. Okay, so let me, okay. So the polynomial code, so these polynomial codes are stabilizer codes, and they're NKD codes. So K here is the same K, right? Because this is the number of basis states we have. N is, well, that's straightforward. There's N things here. And then so the non-trivial thing is D, which turns out to be the minimum of N minus G and G plus 2 minus K. Okay, so for instance, if you want to get the biggest distance, then you should pick N minus G is equal to G plus 2 minus K, which is saying that G is N plus K minus 2 over 2, which you might have to round up or down if this thing is not even. And so that gives us an NK N minus K plus 2 over 2, or nk n minus k plus 1 over 2 code, depending whether n minus k is even or odd. Okay? And so in particular, in the case where k is equal to 1, we're getting a code that's basically, the distance is roughly half of n. So that's why these codes are interesting, because they can get you a very high distance, right? Okay, are there questions on the definition of these polynomial codes? Yeah?
Sorry, what's the difference between the two things you wrote? Oh, is that plus
These,
1 and plus
yeah, sorry, it's too small. This is plus 2, and this is plus 1.
Okay, thank you.
So it's just even and odd cases. Yeah?
Do you have an example?
Yeah, I mean, it's easy to write down examples, but unfortunately, they tend to be a little bit ugly. I mean, so this 312 code that I wrote down, I mean, there is a, so if you let n equal 3 and k equals 1, then you do get distance 2 here. So you're going to get something that's kind of equivalent to that. But if you just kind of write out the stabilizer for this thing, then it will be a bit uglier than that, right? It won't just be x, x, x. It'll be some powers. So it's equivalent up to kind of local unitaries, but it's not as nice. Yeah, sorry. Oh, yeah. So actually, yeah. So I could say that actually that particular example is not even going to work with this exact construction, because I insist that p is greater than n, and that has p is equal to n. There's a variant of this construction that will work, but there's also an analog of that for higher. Yeah. I mean, I guess I can also say that if you so for large enough p, so for p bigger than 5, you can plug in n equals 5, k equals 1, and again you're going to get a distance 3 code. But that's actually something that's inequivalent to this 513 code here. It's actually a different thing. Okay. I guess maybe I won't completely prove this property about the distance, but let me give you an idea of it. Yeah.
So does it matter which alphas we pick? It's just any?
It doesn't matter so long as they're not 0 and they're all different. Okay. So why can't they be 0? Well, if you evaluate the polynomial at 0, then you just get c sub 0 out, right? Which is equal to a sub 0. And you don't want to have the a sub 0 exposed as one of the registers, right? Because then, for instance, it would be easy to dephase that qubit, right? That logical qubit, because if you measured that particular physical qubit, you'd find out the value of the logical qubit. And so you could do that just by acting on one qubit, right? So that would be bad for the distance. And it's not really worthwhile having two things that are the same, because then you get kind of redundant information. And so let's think about how good this is as an error correcting code. So if you remember, it's this CSS construction. We're taking a superposition over elements of some classical code, which is what you get if you kind of ignore the sum and the ket. So you have this classical code that's consisting of different polynomials evaluated at these points. And so how good a code is that classical code? Well, it's actually very good at correcting erasure errors, because a polynomial of degree g is completely determined by its value at g plus 1 different points, right? So if you if you erase n minus g plus 1 registers, n minus g plus 1 physical qubits, then you'll still be left with enough information to completely reconstruct the polynomial. So the classical code has distance n minus g plus 1. You can erase n minus g plus 1, which means that the distance is n minus g. So that's why we're getting this minimum, right? It's a CSS code. So one of them is coming from the distance of this first classical code. And so the second one is a little harder. And so that's the dual code. And so C2 perp is the code that's defined as polynomials of degree up to g with the constraint that Cj is equal to 0 for low degrees. And why is that? Well, because if you look at two different polynomials in this sum, they have the same coefficients for j less than k. And so the difference between them is a polynomial as well, but it's a polynomial with these low coefficients all 0. Right, if you subtract off the two polynomials. Okay, so if we look at that code, then you can work out that, and this is a little more complicated, but you get, if you write down the generator matrix for the dual code, which is the parity check matrix, the original code, what you want to work out is how many columns are independent. And it turns out that that's a Vandermonde matrix, so there's a Vandermonde determinant, which tells you that this many columns are linearly independent. Yeah, sorry. This is the minimum number that are linearly dependent. So that's the distance of the dual code. Okay, so I realized that's not really a proof, but it kind of gives you a flavor of why you get this value. Okay, so one more thing then about QDIT codes. Actually, let's put it up here. So we can also, of course, define a symplectic form for these QDIT codes. And so again, we're going to think of x as 1, 0, and z as 0, 1. Okay? And so therefore, and then x to the b, z to the c will be b, c. Right? So therefore, the ignoring phases, the general element of the Pauli group on n QDITs will be some 2n dimensional vector over z mod p. The symplectic form so if we have two such things, we have, I guess, is going to be b dot c minus a dot d. And this is equal to 0 if and only if the corresponding Paulis commute. Okay? So in this case, you have to, if you want to get everything right, you have to get the order of these things right. And the minus sign matters now, as I said before. And the thing is that you can use this, it's actually a little bit more powerful than just saying when they commute or not. Because it tells you what factor of omega you get, what power of omega you get when you actually move these two polys past each other. Okay? And so using the symplectic representation, it's easy to define the CSS construction. So again, we have two classical codes. C1 perp is a subset of C2. And then the stabilizer in symplectic representation has this form, where H1 and H2 are the parity, the d-dimensional parity check matrices for C1 and C2. Okay? Okay, so so that was the sum of what I wanted to say about QDIT codes to start with. So are there any questions about that? Yeah.
Is there an analog like GF4 for the general poly groups? Like
yes. That gets to be much more complicated. Well, not much more complicated. So, so again, for d equals p, then z mod p is a field, a finite field, and you can create a field extension to have GFP squared. It's again a finite field. The part that's, and then you can line up in the same way. You have the base field is inside this GFP squared. And so you can let, x be 1, for instance, and then z be the omega analog that you're joining to the base field to get GFP squared. And then x to the a, z to the b is going to be a plus b times omega. So that's fine. That gives you all the elements of the field. That part is all the same. The part that's tricky is the generalization of this symplectic form. So the specific things that we did for qubits don't work anymore. You need to come up with some other formula. And there's a little bit of, in order to make this right, it turns out that the definitions of what I just gave you of how to line these things up is probably not the best way to do it. And so it's a little more involved. I think it's in the book how to do it. Yeah.
Are there like any QDIT codes like for maybe these 3 or 5 that you get like n is equal to 3 or 2, something like that for 1 qubit error?
Sorry, so what's the question? So you have n equals 3. So the question is, can you do better than a 513 code? Yeah. Can you do a 313, for instance? Like that. Okay, that's a good question, and that's basically the next topic I want to do. So, but let me first see if there's any more questions on this. Okay, so yeah, so let's think about that. So how good quantum error correcting codes can we make? Even for qubits, I just told you that 513 was the best code to correct one error. How do we know that's true? And even if it's true for qubits, can we do better than that for QDITs? So let's start to think about how we would derive some bounds on the performance of quantum error correcting codes. In this case, well, there's going to be upper and lower bounds, in fact. So one thing, certainly when I started thinking about this, the first thing I thought about was focusing on non-degenerate codes. And so there's a kind of very straightforward bound you can come up with for non-degenerate codes, which is to say, well, for non-degenerate code, every error acting on every basis code word has to give you some different state, right? So in particular for stabilizer codes, you can say, well, each error syndrome can represent a different error. but there's only so many error synchromes, right? There's 2 to the n minus k for qubits, 2 to the n minus k different error synchromes. That has to be at least as big as the total number of errors that we have, right? And so that sets a bound on n and k. And you can make the same argument, in fact, even for non-stabilizer codes. So the quantum error correction conditions say this. And so for non-degenerate codes, CAB is a non-degenerate matrix, right? It has maximum rank. And what that means is that all the states EA psi I are linearly independent. And so we can do, again, some counting, right? We say how many such states are there? Well, for qubits, let's restrict to qubits for the moment. So there's 2 to the k basis states. And how many errors are there of weight t? Well, there's we're going to sum over the weights of the possible errors. And so for errors of weight s, there's n, choose s, places that those errors could occur. Right? So you're selecting out of the n qubits, s of them, that are going to have errors on them. And then how many different kinds of errors are there on a specific set of qubits? Well, the first qubit could have an x, a y, or a z. The second qubit also an x, a y, or z, and so on. And so there's 3 to the s possible errors. So this is the total number of errors. And so what we find is that this times 2 to the k has to be less than or equal to the dimension of the full physical Hilbert space. Otherwise, it's not possible to have all of these vectors be linearly dependent. Okay, and normally it's nicer to rewrite it with the k on this side. So we're saying the total number of errors here has to be less than or equal to 2 to the n minus k. And this is called the quantum Hamming bound. And it's for a non-degenerate n 2 to the k, and sorry. And so distance here is 2t plus 1 code. Okay? So does that bound make sense to people? And so if you want to do this for q dits, what do we change? Well, q dits. So obviously this 2 to the n minus k is going to become a d to the n minus k. And maybe slightly less obvious, this 3, what does it become? Well, remember I got it by saying it could be x, y, or z. So now it could be any Pauli for qubits except for the identity. And how many Paulis are there? There's d squared, right? You have x to the a, z to the b. And so a and b can be anything except both 0. And so this becomes then d squared minus 1 to the s. Otherwise, the bound is the same. Okay? So for qubit case, there's kind of, so this bound is saturated for the 5 qubit code. So that immediately tells you this is the best non-degenerate code to correct one error. And it turns out there's a whole family of such codes for t equals 1. Sorry, for t equals 1, codes to correct one error. There's a whole family of codes for larger n and k that saturate this bound. But you might say, but this is only for non-degenerate codes. Maybe we can do better for degenerate codes. Right? So let's think about that. So it turns out you can't in that particular case. It's actually unknown whether you can ever do better for non-degenerate codes than the quantum Hamming bound. So this is called the quantum singleton bound. It's also, I should say, called the Nil-Laflamme bound because it was first written down by Manny Nil and Raymond Laflamme. But it's kind of more common, I think, to call these by quantum Hamming bound, quantum singleton bound, because they're complete quantum analogs of some classical bounds called the Hamming bound and the singleton bound. And the third one is similarly a classical analog of a quantum analog of a classical bound. And so what the quantum singleton bound says is that an n 2 to the k d code must satisfy the following inequality. K is less than or equal to n minus 2 d minus 1. Okay? And so in particular, the special case of k equals 1 tells you that, so it tells you that n, so implies that n has to be greater than or equal to 2d minus 1. And so if you want d to be equal to 3, n has to be greater than or equal to 5. This immediately proves that 5 qubit code will be the best. And in fact, that case of k equals 1 is a particularly interesting and easy case to prove for this quantum singleton bound. Why? Well, let's think about k equals 1 and think about correcting erasure errors. Okay, so suppose we have these n qubits here, and we want to correct erasure errors. So we can correct up to d minus 1 erasure errors. Now suppose d was n was actually just equal to 2 times d. Sorry, is that what I want? As n, sorry, is equal to 2d minus 2. Right? So it's not satisfying this bound. Okay, so in particular, 2 times d minus 1. Remember, I said I can correct d minus 1 erasure errors. So what I could do is I could take these d minus 1 erasure errors, divide up the qubits into two sets, and each one of them has d minus 1 qubits in it. Right? And now I can correct for the erasure of either set, right? Because I can correct arbitrary d minus 1 erasures. So I could take this set and get a copy of the logical qubit. And I can take this set and get another copy of the logical qubit. And these are totally separate operations because they're involving different qubits. So I can do both of them at the same time, which is a violation of the no-cloning theorem. Okay? So that proves the k equals 1 case. Okay, did everyone follow that? Okay, so the the bound is a bit harder to prove for larger k, but it's not so bad. So so for larger k, n is definitely going to be bigger than this, right? And so let's divide now into 3 sets. So we have two of them are going to be of size d minus 1. So those are going to be A and B. And then we're going to have some left over. And we'll call that set C. Okay? So that has n minus 2d minus 1. And basically what I want to do is I want to prove a bound, lower bound on the size of C. Okay, and to do this, I'm going to look at the entropy. But I guess first what I'm going to do is I'm going to add a reference system. And this is going to have k qubits in it. And then I'm going to have a maximally entangled state between R and the code space. Okay, so there's k logical qubits, so I can make a maximally entangled state, and then of 2k qubits, and then take k of them, halves of the maximally entangled state, and encode them using the quantum error correct encode. Okay, so that's what I'm going to do. That's my state. Okay, so so the first thing to note is that we can correct for the erasure of the set A with this error correct encode, right? Because it's size d minus 1. And so what that means is that A and the reference system have no correlations, right? Because this reference system kind of, well, okay, so suppose we took the rest of it and we reconstructed the original state, right? We decoded. We can do that. Then we get a state that's maximally entangled with R. And therefore, this A qubits that were left over that we didn't use at all had to be in a tensor product with R. Okay, because the maximally entangled state can't be entangled with anything else by monogamy of entanglement. So we know that the density matrix of AR is actually a tensor product. So this is when we trace out B and C. And similarly, we have that we can correct for the erasure of B, so we know that rho BR is rho B tensor rho R. Okay? So now we want to look at the von Neumann entropy of various subsets. So I don't know how familiar you are with that. So the von Neumann entropy is defined as, for any density matrix, it's minus trace rho log rho. And it has various properties, of which I'll be using just some of the basic ones. But I can state them when they happen. So yeah, if you're not familiar with it, you'll just have to kind of take these properties for granted. But it's a good thing to learn. I mean, it's something that shows up again and again and again. Okay, so so the first observation, am I going to be able to fit on here? Maybe. Okay, so the first observation is that we have globally a pure state. Okay? And what that means is that the entropy of AR of rho AR in particular is equal to the entropy of BC. But AR is a tensor product, right? Rows. So that means that the entropy is additive between this tensor product. So this is equal to S of A plus S of R. And moreover, we know the entropy of R. R is half of a maximally entangled state. So its density matrix is maximally mixed. So the entropy is maximum, which is K. So then the next thing we can say is that S of BC, we can use a property called subadditivity. This is one of the basic properties of entropy. This is not strong subadditivity. That's a much more complicated property. Well, much more complicated to prove. This is just subadditivity. And it says that the entropy of a joint system can be at most the entropy of B plus the entropy of C. So this is a very intuitive property. So entropy kind of measures the amount of randomness, you could say, in the state. And so the amount of randomness in B, the randomness in C, kind of maximizes the randomness for the joint state. It can be less, because you can have correlations or entanglement, but it can't be more. Okay, so putting this together, we find that K is less than or equal to S of C plus S of B minus S of A. That's what this inequality has gotten us to. Okay, K being the entropy of R. But of course, this was an analysis for A, but B works just the same way. Right? We could have looked at S of BR instead of S of AR and done the same thing. And then we would get that K is less than or equal to S of C plus S of A minus S of B. Okay? So just adding these up, you immediately find that S of C has to be greater than or equal to K. Okay, but S of C, what's the maximum value that the entropy of C can have? Well, it's the number of qubits in C, which is n minus 2d minus 1. Okay? And this is the quantum singleton bound over there. Okay? Basically, I think it's most helpful to think of the quantum singleton bound because it's a generalization of this no cloning bound. This no cloning bound is the K equals 1 case, and then as you add more qubits, it's just saying that n has to increase by the same amount. Okay, so if you plug in the numbers, you'll find that that the 5-qubit code again saturates the quantum singleton bound. But unfortunately, as you look at larger distances, it's no longer true that qubit codes can saturate the quantum singleton bound. So a code that saturates is called a quantum MDS code. Again, some quantum version of a classical thing. And because the quantum singleton bound applies both to degenerate and non-degenerate codes, you know that if you have a quantum MDS code, it really is optimal. You're definitely not going to be able to do better than that. But you can't for qubits, except for the 5-qubit code and for some distance 2 codes. Now, you can also generalize the quantum singleton bound to qubits, and it's very straightforward. Let me write it down. Here it is. Okay. The only thing you have to do is change the code that you're using. So it's n p to the k for prime dimension d sub p. Right. So it's really the same, and this same proof applies. It's just, I wrote it down for qubits, but I could just as easily have written it for qubits. I mean, I wouldn't have to change anything. Every argument is the same. Okay. And so this is one way you can see that the polynomial codes are interesting, because let's look at them. So so this is D. Let's see. So I guess probably this is the case that's the interesting one. So so 2 times d minus 1 for polynomial codes is n minus k plus 1. And so that's, where is it? Here. So n minus k is, sorry, this is 2 times d. What do I do with the eraser? I guess I don't need it. So 2 times, so this is 2 times, this is d, so, no, wait. Let me try this again. 2 times d is n minus k plus 2. And so 2 times d minus 1 is this minus 2, which is n minus k. Sorry, now I got it right. And so you see that n minus k is, in fact, not just greater than or equal to 2d minus 1, it's equal to. Right? So that's saturating the quantum singleton bound. These polynomial codes are quantum MDS codes. They're the best. They're optimal. Right? You can never do better than that, given the appropriate value of p. Right? They only exist for large enough p. But this is showing you that as you get larger and larger p, you have more and more optimal codes. Okay, so again, that's a reason to go to bigger qubits. Now, the reason not to go to bigger qubits is that they're more complicated. They're more difficult to deal with. There's more things that can happen. I mean, it's not clear it's even fair to compare the distance of a qubit code with a qubit code. Right? There's d squared errors instead of d errors. But maybe even that's not the right comparison. But at least sometimes, under certain circumstances, you definitely be able to win. And if you're not interested in error correction so much, but in some other kind of combinatorial application of quantum error correcting properties, then this is very interesting. Okay? So any questions on the quantum singleton bound? Okay, so the next bound I want to show you is actually, so these were all upper bounds that said you can't do quantum error correcting codes that are better than this. But the next bound I want to show you is actually a lower bound, which says that there exist quantum error correcting codes that are at least this good. Okay, so this is called the quantum Gilbert-Varchamov bound. Again, a quantum analog of the classical Gilbert-Varchamov bound. And so, so suppose we have n, k, and d such that sum s equals 0 to d minus 1, n q's s, 3 to the s is less than or equal to 2 to the n minus k. Then there exists an NKD code. In fact, what I'm going to show is that there exists a stabilizer code with these parameters. Okay? So let me point out that this looks very similar to the quantum Hamming bound, but it's not quite the same. Wait, did I just hide the quantum Hamming bound? Yeah. So the quantum Hamming bound is almost the same, but it's a sum goes from s equals 0 to t. And now I'm taking the sum from s equals 0 to d minus 1. Okay, so d minus 1 is 2 times t, right? So we're summing over not just the errors that we want to correct, but kind of all the errors that we should be able to detect with this code, or erasures that we should be able to correct. And so this is gives you lower numbers for NKD, of course. But the nice thing is that you know that when you satisfy these numbers, then the code definitely exists. So let's think about how this behaves. Oh, and yeah, for QDITs, you can again make the same thing, right? Where this is d to the n minus k and d squared minus 1 to the s. Okay, so let's focus on the case where n goes to infinity. And we're going to so if s over n is constant, then this binomial coefficient n q's s approaches 2 to the n h of s over n, where h is this binary entropy function. H of x is x log x minus 1 minus x log 1 minus x. So you can just derive this using Stirling's approximation, you know, on the factorials. Okay, and so based on that, we see that the Hamming bound becomes k over n is less than or equal to 1 minus t over n log 3 minus h of t over n. And the Gilbert-Wassermann bound works when k over n is less than or equal to 1 minus d over n log 3 minus h of d over n. Okay. So if you plot, do I want to do this way? So if you're plotting d over n here and k over n here, qualitatively speaking, the quantum Hamming bound will look like something like this, and the Gilbert-Wassermann bound something like this. Okay, and so you know that there exist codes in here. Here, there's no, at least non-degenerate codes. And then in here, you don't know. There's a few codes that are known in that regime, but not by this construction. And then the quantum singleton bound is a line that's just kind of like worse. Sorry, this shouldn't be 1 then if we do this. This goes to 0 at, this is the singleton. Goes to this goes to 0 at d is half n. Okay? Just to kind of give you an idea of how these different things relate. Okay, so let's prove the Gilbert-Verschamer bound. Okay, so what we're going to do is, we fixed n and k, and so what I'm going to do is I'm going to make a list of all. I mean, this is hypothetical. Obviously, you're not going to do this in practice. I'm going to make a list of all stabilizer codes that have k logical qubits and n physical qubits. Okay. So we're going to have code, S1, S2, S3, to some very large number. So let's say there's big N of them. Okay? And then for each code, I'm going to make a list of all of the errors that this code detects. In other words, the things in N of S minus S. So it's going to be, all the polys. So E1, E2, E3, E1 prime, E2 prime, E3 prime, and so on. So this is N of S minus S. And so what I'm going to do is I'm going to go through this list of stabilizer codes, and I'm going to cross off all of the codes where N of S minus S contains something of low weight less than or equal to, less than D. Okay? And what I want to show is that there's still some codes left over after I do this, when the Gilbert-Verschamer bound is satisfied. Okay, which seems kind of crazy, right? I mean, there's lots of codes, but we're crossing off so many of them. But actually, it turns out there's even more codes that when the Gilbert-Verschamer bound, there's even more codes than the number of things we're crossing off. Okay, so how many codes are we crossing off? Well, so it turns out, so what we're going to do is we're going to go through each low weight error. We're going to say, OK, X on the first qubit. Let's cross off all the codes for which N of S minus S contains X. OK, then we'll do X on the second qubit, and Z on the first qubit, and so on. And it turns out that each poly is in N of S minus S for the same number of codes. Okay, so how do I know that? Well, the way I know it is actually something I haven't explained to you yet. It uses the Clifford group, which is a symmetry group of the poly group. And I'll at least get started on talking about the Clifford group at the end of this lecture. So, but the upshot is that there's a total symmetry between everything in the poly group. So anything that's not the identity acts the same way. And so there's some symmetry group that will take, for instance, X on the first qubit to Z1, X2, Z3, Y4, et cetera. And that same symmetry will map the list of stabilizer codes that detect X1 to a list of the same size that detect this other complicated error. Okay, so every error, whether low weight or high weight, is detected by the same number of stabilizer codes. And so let's call this C. Okay, and so let's try to figure out what C is. Well, I don't want to work out exactly, but I'm going to do it in terms of n. So let's look at this set of all the possible errors here. So every error appears in C different lists here. So, so how many errors are there? Well, there's 4 to the n minus 1, right? That's just ignoring phases. That's the size of the non-identity things in the poly group. And so the total number of things that must appear over here in this table is C times 4 to the n minus 1. Okay? But that's one way of counting the number of things here. The other way of counting is to say, well, how many codes do we have? We have n codes. And each code can detect how many things in n of s minus s. Well, n of s, remember n of s mod s is equivalent to the logical polygroup. So n of s mod s is 2 to the k. And when we multiply by s, we get 2 to the k times 2 to the n minus k. Sorry, the logical polygroup is 4 to the k. So it's 4 to the k times 2 to the n minus k is 2 to the n plus k. Plus phases, which don't really matter here. So n of s is 2 to the n plus k. But then we have to subtract out s, which is size 2 to the n minus k. Okay? So this tells us what c is in terms of n. Okay. So then let's get on to the next step, which is to cross off the codes that have low weight errors that they detect. Sorry, that they don't detect. So how many low weight errors are there? Well, that's something we've already counted, right, for the quantum Gilbert-Rauschenberg bound. So we're going to take the sum of s equals 0 to d minus 1, n choose s, 3 to the s errors. So these are the things that the total number of errors of weight up to d minus 1. And for each one, we're going to go through and we're going to cross off codes from this list. And how many codes do we cross off? Well, we cross off at most C codes. It's actually going to be less than that because some of them will be codes that we already crossed off. So we'll cross them off multiple times. So let's just call this B for simplicity. And so we have B at most, okay, number of codes gone is less than or equal to B times C, which is B n 2 to the n plus k minus 2 to the n minus k over 4 to the n minus 1. And so factoring out a 2 to the n minus k, we get bn 4 to the k minus 1 over 4 to the n minus 1. And so with a little bit of arithmetic, you can show that this is less than, let me finish for a second. This is less than or equal to 1 over 4 to the n minus k. So this whole thing is less than or equal to, is less than bn 2 to the n minus k over 4 to the n minus k. Which implies that, we've crossed off at most bn times divided by 2 to the n minus k codes. Okay, question.
Is 4 to the n minus 1 just n of s? Or is that?
4
to the power of n minus 1, isn't that include all?
So this is the number of all non-identity polys.
Okay, right. And on the right side is...
So the point is that the list of undetectable errors, some of them will be low weight, but some of them will also be high weight. Right? Because everything in n of s minus s, we're gonna list here. And so all of these errors have to appear on this list somewhere, and then they appear at c times. And so the total number of errors that are written down in this picture is c times this, 4 to the n minus 1.
Okay, but an error can also be s though? Because all non-identity polys include s, right?
I'm just writing down the things that are in n of s minus s.
And on the right side, is also n of s minus s?
Yeah, so so how many things are in n of s minus s for a particular stabilizer? It's 2 to the n plus k. So n of s is 2 to the n plus k. And then when I subtract off the things that are in s, that's 2 to the n minus k.
Okay.
So that's why I get this difference. Okay? Okay, so anyway, so the number of codes we've crossed off is at most this number. Okay, and if if B, therefore, is less than 2 to the n minus k, then we haven't crossed off n, big N codes. So there's some codes left. Okay? And those codes have nothing of weight d minus 1 or less in n of s minus s. And therefore, their distance is at least d. Okay? So the other thing about this argument is, in fact, shows something even stronger. Because for large, if you're in that asymptotic regime of large n and k, B is going to, this ratio B over 2 to the n minus k is going to scale as 1 over 2 to the epsilon n, where epsilon is kind of the difference between this side and this side. Which means that not only are there codes left over, but almost all of the codes are left over. Right? So if you pick a random code for large n, and you're below the quantum Gilbert-Rajkumar bound, with very high probability, it will have a good distance. Okay? But despite this, it's still very hard to write down codes with good distance. Because writing down a random code, first of all, it's hard to check that the distance is actually good. You might have gotten unlucky. You can write down a random code, and most likely you'll be okay. But you can never really be sure until you've gone through and checked. And then it's, of course, hard to deal with a totally random code. It's hard to do error correction and whatnot. Okay, so are there questions on that? Okay, so I think we should take a break here. Let's make it a 10-minute break. And then when we come back, I'll tell you quickly about one more class of bounds on quantum microwave codes, and then we'll talk about the Clifford group. Certainly I know experimental implementations that could use QDITs. Maybe the most obvious thing is there's various QKD implementations that use very high dimensional states of light. For computation, yeah, I'm not sure. In a lot of cases, it would be kind of straightforward to make it a QDIT, but or at least straightforward in the sense that doing anything is straightforward. But
straightforward, like as a clear efficiency.
Yeah, that's right. It's not fundamentally different from what they would be doing anyway. Like in the ion trap, you just use 3 states instead of 2 states, right? You need more lasers, and the gates are more complicated, and everything's more complicated. But yeah. So I guess one way that QDIT quantum error correcting codes can be used is if you concatenate. You can use them as ways of constructing qubit codes by kind of combining 2 different codes. One of them is a QDIT code, and one of them is a qubit code. And there's other approaches you can do as well. Okay. Are there other questions?
So when you say you pick a random code,
right?
What is the thing you pick at random?
What is the thing you pick at random? So in this context, I guess you'd pick a random stabilizer. So you could just kind of pick random generators with the constraint that they commute with the previous ones. That will give you a uniformly random stabilizer. Okay. So let's. So the bounds that I've showed you are kind of the simplest ones to write down and to prove. But unfortunately, they don't actually give you a very tight restriction on codes that actually exist. So, I mean, that was most obvious with the singleton bound, where it's certainly the case that there do not exist codes saturating a singleton bound for many, many parameters. But even for the quantum Hamming bound, we only really know, for distance 3, we know an infinite family of codes that saturate it, but for larger distances, we don't. And it's not totally clear to what extent that's the limit of what we can do. But certainly there's very specific cases where using some more advanced machinery, you can prove tighter bounds that actually let you determine whether a code of those parameters exists or not. In the sense, I mean, proving that it exists is a totally different procedure. You have to actually find a code. But proving that it doesn't exist, you can tighten the bounds based on from what we have so far. So I don't want to go into the details about how you do this, but I do want to show you one tool which is fairly powerful and kind of neat. And so this is the idea of linear programming bounds. So yeah. So for instance, I told you before that there was no 312 error correcting code. So how do I know that? I know it via these linear programming bounds. And so what I want to do is so what it's going to do is these bounds are going to take advantage of something called the weight enumerator of the code. So for stabilizer code, you can look at the number of elements of the stabilizer of a given weight, of different weights. Number of elements of weight 1, number of elements of weight 2, number of elements of weight 3, and so on. And there's a formula you can write down that relates this to the distribution of weights in n of s. Okay? And it turns out that this formula actually can be generalized to not just stabilizer codes, but to general quantum error correcting codes. And so that's what I'm going to do. I'm going to write it down for you. Okay. So first, let's generalize the number of elements to the stabilizer of a given weight. So we have an NKD code. Pi is the projection onto the code space. And so we're going to let A sub j equal 1 over k squared, sum of Paulis with weight j. Then take the absolute value of trace p pi and then square the absolute value. Okay, we're summing over this. Okay. Then if the quantum error correcting code is a stabilizer code, Aj is the number of elements in S of weight j. So I don't want to go through this. Sure. Okay. So to prove that, so we write down this projector. So remember, we had this formula for the projector onto the code space for stabilizer code. And so remember also that trace of a poly is 0 unless it's the identity. So AJ is, so big K here is 2 to the little k. So this is 1 over 2 to the 2k, 2 to the 2n minus k when we evaluate this. Sum of trace, I seem to find the lowercase trace, of this thing. And this, so there's the sum we can take outside of the trace, and trace of Pm gives us 0 unless P is equal to M. Right? So this is a sum over P. And so basically this, yeah. So this then is equal to, so the 2k here and the 2, so we get 1 over 2 to the 2n, the 2k and the 2 to the n minus k combine, and we get sum over p of, so in here, we're going to get something where dp is equal to 0 if p is not in the stabilizer, because we run over this whole sum and we never get p. But if p is in the stabilizer, then there's going to be one value of m for which this matches, and then the trace is going to be the trace of the identity, which is 2 to the n. Okay? Sorry, it's 2 to the, the trace is 2 to the n, and then we square it. So it's 2 to the 2n. Okay? And so what this is saying is that this sum is giving us 1 whenever p is in the stabilizer, and 0 otherwise. And so we just get the number of elements in the stabilizer. Okay? Okay, so that was the generalization of the number of elements in the stabilizer. And now let's do it for the normalizer. So similarly, NKD code, we're going to let B sub j is equal to 1 over big K sum polys of weight j. And take, now we're going to take the trace of P pi P pi. And then for stabilizer code, Bj is the number of elements of weight j in N of S. And so basically, it's kind of the same proof, but there's a little bit different. So the main difference is that, so instead of this trace of PM, we're getting things of the form PM prime, because we have two projectors here, and so we have two sums over elements of the stabilizer. And so this thing, well, the polys commute or anti-commute, so we can always move this M past the P, getting a plus or minus 1. And then the P's will cancel. And so this is going to be is equal to trace plus or minus trace of M prime. And so we have to, so we get 0 unless M is equal to M prime. And so one of the sums of the stabilizer disappears. But when they are equal, we're going to get something non-trivial. So what are we going to get? We're going to get plus 2 to the n if P and M commute, and minus 2 to the n if P and M anti-commute. Right? So now let's think about it. And remember, we're summing over all elements M in the stabilizer. So if P is in N of S, then that means we only ever get this case. Okay? But if P is not in N of S, well, then sometimes we'll get plus and sometimes we'll get minus. And you can work out that actually you get plus half, it'll commute with half the elements of the stabilizer, and anti-commute with half of the elements. And then the plus and minus cancel out. So the sum gets 0. Okay? And so the upshot then is that we're only summing over, that when we do this sum, we get 0 except for the elements that are in N of S. And so by the same kind of argument, you show that it's equal to the number of elements in N of S. Okay? I realize I didn't go through all the details of that, but that's the basic idea, the important elements of the proof. Okay? Okay, and so then, so using these things, we can define these weight enumerators and what's called the dual weight enumerator. So the weight enumerator is a polynomial a of x, which is equal to sum of j equals 0 to n. So you're summing over all the possible weights of aj x to the j. So this polynomial kind of encodes the weight distribution of the stabilizer. And the dual weight enumerator b of x is the same thing for b. And so again, for stabilizer code, this encodes the weight distribution of n of s. Okay, and so we have the following properties for these things, which, well, there's 3 of them that are fairly straightforward and 1 that's very non-trivial. So the first property is that the 0 components are all 1. B0 is equal to A0 is equal to 1. So for stabilizer, this is obvious, right? Because this is the number of things of weight 0, which is just the identity, which is always in both S and N of S. And similarly, the second thing, which is that Bj is greater than or equal to Aj, is greater than 0. This is also obvious for the stabilizer, right? Because, well, first of all, they're the number of things, so they have to be non-negative. And S is included in N of S. So the number of things of weight J in N of S has got to be greater than or equal to the number in the stabilizer. And so this one is talking about the distance. The distance of the quantum error correcting code is the minimum value of J for which Bj is not equal to Aj. Okay. Again, for the stabilizer, this is pretty straightforward, right? So the distance of the stabilizer code is the minimum weight element in N of S minus S. So when Bj is equal to Aj, then there are no elements of that weight in N of S minus S, because everything that's in N of S is also in S. And when they're not equal, then that means that there's something in N of S minus S. Okay. Then finally, this thing is called the quantum McWilliams identity. Again, a generalization of a classical thing. So it relates these two weight enumerators. So it says that B of x is equal to big K over 2 to the n, 1 plus 3x to the n, A of 1 minus x over 1 plus 3x. Okay, so that's not obvious at all. But it turns out to be true. And so then what you can do is, so this formula here gives you some complicated but linear relationships between the AJs and the BJs. And so if you want to try to prove bounds on the existence of quantum error correcting codes, you can write down all of those formulas along with these constraints. And then it's a big linear programming problem. For what values, so these constraints, and you say, for what values, well, okay, probably the way you'd want to do it is you'd say, and I want a code of distance d, so then for j less than d, I should have bj equal to aj. And then you'd write down all of these linear constraints, and then you plug it into some linear optimizer, and try to find an integer solution. Well, it doesn't have to be an integer solution, but you have to try to find a solution. And if there doesn't exist a solution, then you know that there can't exist a quantum error correcting code with those parameters. Okay? If there does exist a solution, then you don't know. There might or might not exist a code. It turns out that even these constraints certainly don't completely specify codes. And you can come up with some additional linear programming bounds that will let you narrow things down even more. Yeah, but I don't want to spend too much time on that because we have a lot of other stuff that I'd like to do in the class. But this gives you an idea of how you can get these more advanced bounds and to prove more things about codes. So there are questions on that.
Make one comment.
Okay.
Is with this you can show that there's no degenerate 5-qubit code.
Yes. So it's a little more complicated, actually. So it turns out that so in the case of a stabilizer code, a non-degenerate code is going to have an even stronger condition, right? Which is that bj is actually equal to 0 for j less than the distance. And so then this case where they're equal but greater than 0 for a stabilizer code is the case of degenerate codes. But the thing is that for non-stabilizer codes, it's actually not the same as degenerate versus non-degenerate. It's some other distinction, which is called pure versus impure. And so what you're actually showing is that there's no pure codes, 5-qubit code in that case. Sorry, no impure 5-qubit code. And actually, it turns out there's an even stronger statement you can prove without using these things, which is that any 5-qubit code, 513 code, is equivalent up to local unitaries to the 5-qubit code. So actually, it's a unique thing. So yeah, that also shows it. But one thing you definitely can show using this is that there's no 312 code, right? So this is how you can show that these two trig codes are actually better, for instance. Okay. Other questions on this? Okay, so then I want to move on to a different topic, which is symmetries of stabilizer codes, which is kind of starting to do the transition into talking about fault tolerance. Can I get that one down? Okay. So obviously the Pauli group is playing a big role in the theory of stabilizer codes. And so when we start to talk about fault tolerance, we care about unitaries and how they interact with stabilizer codes. There's a couple of different ways you can approach this subject. One of them is to say, well, I want to know the kinds of unitaries that are useful for encoding stabilizer codes. Another question you can ask is, suppose I want to do gates on stabilizer codes. What's a natural set of unitaries to look at first? And so in particular, so stabilizer codes are defined as eigenstates of a bunch of Pauli operators. So suppose we do some unitary to such a state. So we have a state in a stabilizer code, and we apply U to it. So if psi is in the stabilizer code, then psi is equal to m psi. So this is certainly true. And then I can insert a u dagger u here. So I have u m u dagger, u psi. So that's true as well. And what this is showing is that psi was an eigenstate of m, implies that u psi is an eigenstate and a +1 eigenstate at that of u m u dagger. Okay? So what that means is that if I have a stabilizer that consists of a whole bunch of m's, and I apply u to a code word, then the new code word is going to be an eigenstate of a new stabilizer where we transformed m to u m u dagger. And so we'd like to restrict attention to the cases that this new stabilizer is also composed of elements of the Pauli group. Okay? So so we want to look at the cases where this thing is in Pn, when for m in Pn. So we're going to define a group of unitaries that has that property. Okay? So I'm defining it as a set of unitaries that conjugate the polygroup into itself. So that's, in group theory notation, it's the normalizer of the Clifford group in the unitary, of the polygroup in the unitary group. So let's see. So, I mean, I'm just asserting that it's a group, but it's easy to check that. So if U is in the polygroup, in the Clifford group, and V is in the Clifford group, then UV poly, so the UV dagger is V dagger U dagger, and so this is U VP V dagger U dagger. And this is in the polygroup, and therefore this is in the polygroup as well, by the properties, by the fact that U and V are in the Clifford group. Okay? And so the other thing is if UP U dagger is equal to Q, then that implies that U dagger Q U is equal to P. And since, and so this shows that U dagger is also in the Clifford group when U is in the Clifford group. And so these two properties tell you that it's a group. So frequently, so the way I've defined this, it's used in U of 2 to the n, and that means that any kind of constant phase out front, e to the I phi times the identity, is also going to be in the Clifford group. And so mostly I'm just going to ignore that global phase. It's kind of physically unimportant. But to get all the mathematics right, sometimes you have to include it and sometimes you don't. Okay, so kind of one of the main properties of the Clifford group, and the thing that's always worth bearing in mind, is that this conjugation preserves the commutation relation in the polygroup. So, suppose P and Q commute. Well, so UP U dagger UQ U dagger is equal to, if you multiply it out, it's equal to U PQ U dagger minus U QP U dagger. And so PQ is equal to 0 if and only if UP U dagger UQ U dagger is equal to 0. So that's kind of is telling us that the Clifford group kind of preserves this property that we're relying on for stabilizer codes to work, right? It preserves commutation. So if you map a stabilizer under conjugation by Clifford group element, you'll always get something that's another stabilizer, right? It commutes. And similarly, things that were detectable or undetectable errors in the first code will get mapped to things that are detectable and undetectable errors in the image code. Okay, so what are these Clifford group elements? Well, it turns out there are some very familiar unitaries. So let's start with the polygroup. So if you have some poly, what do I want to call it? P, then let's try conjugating another poly with it. So P, Q, P dagger. Well, if P and Q commute, then we can just move the P through. And if P and Q is anti-commute, then we move it through with a minus sign. So either way, we're going to get plus or minus p dagger q, which is plus or minus q. Okay? And so if q is in the polygroup, this is also in the polygroup. And in particular, we get kind of a trivial map if p and q commute. We get a trivial map for the cases where they commute, and a phase of -1 for the cases where they anti-commute. Okay, so conjugation by p kind of switches the phase of half the polygroup. So another thing in the polygroup is the Hadamard. So let's work this out. This one, we're just going to kind of multiply it out. So if you multiply these matrices out, I'll let you do that on your own time if you want to. You get this, which is Z. Okay, and similarly, you can work out HZ H dagger. It turns out to be X. So the Hadamard transform switches X and Z under conjugation, which is something I already kind of told you. Remember in the very first lecture that the Hadamard transform will switch us between the Z basis eigenstates and the X basis eigenstates. So this is a way of kind of formalizing that. So, of course, this is not everything in the polygroup. You could also calculate HY H dagger. But it turns out you don't have to check that to see that H is in the Clifford group. Why is that? Well, Y is equal to X times Z, I X times Z. And we can work this out by sticking in H dagger H here. Okay, and these we've already figured out. So this is I times ZX, which is minus Y. Okay, and it had to be something in the polygroup, right? Because no matter what product we're taking here, we can always insert the H dagger H, and we'll get conjugation of the first thing in the product times the conjugation of the second thing in the product, which are both polys, and so the product of them will be in the polygroup. Okay? Okay, so another example gate is this pi over 4 phase rotation. Okay, so it's a diagonal thing. This is the square root of Z. And so again, you can work out that if you conjugate X, you get a poly, you get, in fact, Y. And since it's diagonal, it commutes with Z. So it conjugates X to Y and Z to Z. So you can start to think of these, what the Clifford group elements are going to do is they're going to permute the polys. And you know they can't take two things to each other. I mean, they can't. It has to be a one-to-one map because this is an automorphism, right? It has an inverse, which is just conjugating by the dagger. So really we are just permuting the elements. And so you can think of Hadamard is taking the X and the Z and switching them. And then Y goes to minus Y, which is a little more confusing. But then this pi over 4 is switching the Y and the Z. And in fact, you'll see maybe next week that you can do any permutation of the polys that preserves commutation relations. So for a single qubit, that means any permutation of X, Y, and Z. For multiple qubits, it's not. But okay. And so then the last example gate is the controlled NOT gate. And the controlled NOT, if you work out, so it's a 2-qubit gate, so we need to look at a generating set of 2-qubit polys. So we're going to look at X, IX, Z, I, and IZ. And then any other poly up to phases is going to be a product of these things. Okay? And so Xi goes to XX, IX goes to IX, ZI goes to ZI, and IZ goes to ZZ. Okay? And again, you can just work this out by multiplying. So notice that we've preserved the commutation relations as we should. So for instance, Xi and Zi anti-commute. XX and Zi on the right side anti-commute. Whereas Xi and IZ commute, and so XX and ZZ commute. Okay? I mean, they had to. We proved that already, but it's good to see it in practice. Okay, any questions so far? Okay, actually I take it back. I see that I did plan to do it today. So when I said you'll find out next week, I actually meant you'll find out right now that the Clifford group can implement any automorphism, any permutation of the polys that preserves the commutation relations. Well, okay. So for us it also has to preserve multiplication. So it's an automorphism. So then there exists some unitary such that UP U dagger is equal to F of P, and U is unique up to global phase. Okay. And so this, I mean, I didn't write it as part of the theorem, but because UP U dagger is always getting a poly out, this implies that U is in the Clifford group. Guess I can write it now. Okay, so the other thing that the proof of this is going to show is that, well, follows from the statement of the theorem already, which is that if you want to specify a Clifford group operation, it's enough to tell you what its action on the polys is, right? And then you can use that to reconstruct the whole unitary up to a global phase, which doesn't really matter. Okay? And in particular, this type of argument shows that you don't actually even have to specify it on all the polys. You only have to specify it on a generating set of polys. And so that's why, for instance, if I can write down this, then this is enough to completely specify the C0 gate up to global phase. Because all the other polys we can deduce by products and so on. Okay? And so you remember that I mentioned that one advantage of stabilizer codes is that they're much more succinct representation of this code than writing it out in these giant basis states. And so by similar token, Clifford group operations, I mean, unitaries, remember they're unitaries on n qubits is in u 2 to the n. So if you wrote that down as a matrix, that's a 2 to the n by 2 to the n dimensional matrix. But Clifford group elements have a much smaller representation because all you have to do is specify their action on 2 times n polys that generate the poly group. And that action is to take it to another poly element. So each image is also a small thing that you can write down. Right? So it basically boils down to a 2n by 2n matrix, roughly. Okay, and so that's an advantage of dealing with Clifford group operations and stabilizer codes, that you have this kind of much more efficient way of writing it than in big 2 to the n by 2 to the n matrices. Okay. So so what we're going to do is we're going to use this property that I started out this section with, of saying that if we started with a stabilizer that had elements m, and then we apply a Clifford group operation, or really any unitary, we end up with something that's eigenstate of the operator is u dagger. Okay, so what we want to do is we want to find some u that takes u dagger to f of p. So for instance, suppose we start out with the state 0, 0, 0. So this has a stabilizer generated by the z's. Okay, and under this map f of p, it gets mapped to f of z1, f of z2, f of zn. And because f of p preserves commutation relations, this is an abelian group. And so this is a stabilizer. And therefore, and so it's a stabilizer, look, it has n generators for n qubits. So it encodes a single state. And so we can call that state, well, we might as well call it u0, right? So it's the image of 0 under u. It's just some state. And so we're going to start to kind of reconstruct the action of u by calling this u times 0. Okay, great. So so that's one state. So now let's look at some other basis states. So what about the state 1 and then all zeros? Well, this is equal to x on the first qubit applied to the all zeros state. So what's this going to get mapped to under u? Well, it's going to get mapped to, so we want it to be u times the all zeros state, which is u x1 u dagger u times the all zeros state, right? So that's this thing here with the u dagger u inserted. And this thing here, we know should be f of x1. So what we can do is we can say this is, we can define u applied to all ones of f as f of x1 applied to this, which is, remember, just some state that we found. Okay? So that defines this state. And similarly, if we have any other basis state, so we're going to get some x's here. And that's going to get mapped to f of this other x Pauli operator applied here. Right. Okay. So, but there's a couple of things that I want to check. So the first thing is we're starting with a basis, and I'm just getting some other states out of here. And so I'm saying that for you to work, these are the things I have to get. But I want to show that U works, right? So what I have to do is I have to show that these other states that I'm getting are actually orthogonal to the original, sorry, not to the original states, but to each other. So, so for instance, we can take this state here, and take its inner product with this state. And I want to be a little careful because I've said that they're U, but I can't actually cancel the U dagger U yet because I don't know that they're unitaries. But I have some state here, certainly. And so what I'm getting here is I'm getting, by this definition, I'm getting this state with an f of x1 in here, and then here this state. Okay? Now this state, remember, is the stabilizer code for this stabilizer, is stabilizer state, the kind of unique state that's stabilized by these things. So, for instance, I can insert f of zi in here without changing anything, and an f of zi dagger in here also without changing anything. Okay. Now, in particular, I can insert f of z1 since I want to do that because z1 and x1 anti-commute. Okay, and f, remember, preserves the commutation relations. So that means that f of z1 and f of x1 also anti-commute. And so what that means is that f of z1 dagger f of x1 f of z1 is equal to minus f of x1 because I can move this through and I get a minus sign. And so this thing is equal to minus itself, and therefore is equal to 0. Okay? So I've shown that these two things really are orthogonal. And similarly, for any two different basis states that you get here, you can show that they're orthogonal. Yeah, okay. So that shows that there actually does exist a unitary that is consistent with this mapping. Now you have to do a little bit more work to show that that unitary that's mapping these orthogonal basis states to these orthogonal basis states, sorry, these orthogonal basis states actually does implement this conjugation transformation as desired, but that's fairly straightforward. I mean, we kind of defined it so that it had to work. And so that proves the theorem, and it also gives you kind of an explicit method, given a conjugation action for the unitary, how to reconstruct the matrix. Right? This is saying what happens to the basis states. Right? Because you know what all of these things are, you know what this stabilizer is, so you know what all zeros go to, and you know what f of x1, et cetera, are. So you can just read off the rows of the matrix that way. Okay? Are there questions on that? Yeah.
So it feels sort of analogous from when we went to the code race to the stabilizers, it's going from the stabilizers to the Clifford group, in that we were able to sort of write this larger system more succinctly with the Clifford group. Does that sort of keep going? Like, is there a group for the Clifford group that does the same thing, and like a Clifford group for that, etc.?
Not exactly. So there's something that will show up later in the course called the Clifford hierarchy. So then the next level of the hierarchy is the things that conjugate polys into Clifford group operations. And these things are interesting from the point of view of fault tolerance, but they're much messier. It's not a group anymore. And we don't actually really even know exactly what's in that set. I mean, there is, yeah, I mean, so you're not really getting any simplification by going from the poly group to a Clifford group. It's getting more complicated, in fact. The poly group is a very simple thing. The Clifford group is more complicated. It has kind of more interesting elements. You get things other than commutation and anti-commutation. But what you're getting in exchange for that is more power. The poly group, only does polys. The Clifford group contains these interesting gates like 2-qubit gates, CNOT gate, entangling gates, and phase gates and stuff like that. And so, yeah. So for instance, I said at the beginning, you can ask one way you could approach this is to say, what are the unitaries that I need to encode stabilizer codes? And the answer is the Clifford group. Why is that? Well, that follows from this theorem that I've just proven. So if I have any, so what do I want to do to encode a stabilizer code? Just an arbitrary stabilizer code. Well, I want to take it from, so I start out with k qubits and n minus k ancilla qubits, which I can start as all zeros. So that's also a stabilizer code, right? It's a stabilizer code with stabilizer z on all of the ancilla qubits. And what I want to do is I want to map that stabilizer to the stabilizer of the code I'm interested in, right? So the first thing is a stabilizer, they commute. The second thing is a stabilizer, look at the generators, they commute. So I can just map them one to the other. In fact, I can go even further than that and say, oh, I want to have a particular logical x and logical z set of operators. Well, I can map x1 and z1 to the logical x1 and logical z1. And that preserves the commutation relation, so there's going to be some Clifford group operation that does that. Okay? I guess maybe I can also point out the missing step in this proof of the Gilbert-Rauschenberg bound. I said all of the polys have the same number of stabilizers that they're detectable by, or undetectable by. Right? So specifically, for any poly, it appears in the same number of things n of s. Well, how is that? Well, I can use the Clifford group to map any poly to any other poly, p to q. And when I do that, look at the list of stabilizers for which p is in n of s. Well, under this Clifford group operation, they get mapped to another list of stabilizers for which q is in n of s. Right? And it's an invertible map, so the list of stabilizers has to be the same length. Therefore, they're detected by the same number of things. Okay? So that's the kind of thing you're getting out of the Clifford group. You're getting the ability to do this kind of argument and to do all sorts of unitaries. Okay, maybe I'll prove one more thing about the Clifford group and then end for the day. So if we like to represent the polys in this binary matrix formalism, the symplectic representation, then the Clifford group element is, well, as we've just shown, you can define it by its action on a generating set of polys, right? Each of which is a 2n-bit vector. So the Clifford group element is going to correspond to a 2n by 2n binary matrix, ignoring phases. And so it turns out that if you take the Clifford group and you mod out the global phases and the poly group, then what you get is this 2n by 2n matrix that are exactly the symplectic binary matrices. So the first thing to think about is this is a kind of linear algebra, and this is group multiplication that we're thinking about. But that's okay, right? Because when we move from the poly group to this symplectic binary representation, group multiplication in the poly group corresponds to addition in the vector space, right? So that's why we're going to linear maps. So the main thing to see is the first claim is that U and U prime act the same on binary vectors if and only if U prime is equal to e to the I phi UP, with P in the poly group. Okay, so this is saying that this coset is really the right thing to look at. So a unique element of this coset, so that if you take an element of this coset, two different elements of this coset, they'll give you the same matrix acting on binary vectors, and that's the only time when you get the same matrix. So this direction is pretty straightforward. So if U prime is equal to e to the I phi UP, well, the e to the I phi is a global phase. It's not going to affect the conjugation action at all. The P does affect the conjugation action, but it does it in a very specific way. It does it by giving us a phase of plus or minus 1. And when we're dealing with binary vectors, we're ignoring those phases. Okay? So this part is okay. We've checked that. That's straightforward. So this part is a little harder. So let's think about U prime, U dagger. So U and U prime act the same on the binary vectors. So U prime, U dagger must act trivially on the binary vectors. And what I want to show is that it must be an element of the poly group up to global phase. So so the thing is that acting trivially on binary vectors doesn't mean it actually acts trivially on the poly group, right? So in particular, it can take P to to plus or minus p in general. And so in particular, we can do the same kind of argument as we did before. And we're seeing that zi goes to plus or minus zi, which means that this stabilizer here is going to be, sorry, here, let's call this V. And so we're seeing that V times all zeros is going to do something that's an eigenstate of plus or minus zi's, which is going to be a basis state, but it might be a different basis state. So let's call that B. And similarly, xi is going to plus or minus xi, right? So that's saying that V times, say, 1 and then all zeros is going to, which is by the same argument, is going to map to plus or minus x1 times this basis state. Let's see. So yeah, so more generally, we have to be a little bit more careful. So we can say that the state x is going to map to so x1 gives us one sign, plus or minus 1, which is going to be some value, and then x2 will give us some other sign. And so let's keep track of all of those. So we're going to say that xi goes to minus 1 to the ci xi, and zi. So this b, whenever we're getting a plus here, we're getting bi is equal to 0, and whenever we're getting minus, we're getting bi is equal to 1. So zi is going to minus 1 to the bi zi, with this b being the same b here. And so if we have some general x, well, then what we do is we write out as a set of bit strings, and we get x1, x2, x3 to the appropriate bit value. And so what we're doing is we're getting minus 1 to the c dot x, and then b plus x. Okay? Which is what you would get if you applied right, xi to the bi and zi to the ci to the basis state x. Right? Because zi to the ci will give you a phase of minus 1 to the xi dot ci, xi ci. So that's this term. And then xi to the bi will add b to the ith bit. So this is this, and this is therefore saying that this action is a Pauli. Okay? Yeah, okay. So that proves the theorem, and it gives us this nice characterization in terms of symplectic group. And so you can do, again, if you're willing to ignore the global phases, you can do lots of calculations about the Clifford group by writing down these binary symplectic matrices and just multiplying them. then at the end of the day, you kind of do care about the phases because the global phases don't matter, but the Pauli group does matter, right? It actually changes the result. So you have to put back the Pauli group in the end. But usually that's much easier. Okay. So, are there any questions? Yeah.
You define the Clifford group for qubits. Is there an analogous one for QDITs?
There absolutely is. So the definition is the same. It's just, again, the set of things that conjugate the QDIT Pauli group into itself. The real difference comes up when you look at these examples. Yeah, I might give you some exercises on this next week. I haven't decided yet. Well, we'll see. The upshot is, so it's still true that the QDIT Paulis are in the QDIT Clifford group. The Hadamard gets replaced by the discrete Fourier transform, mod P. And that takes, I believe, x to z and z to x inverse. And if inverse Fourier transform will have the inverse on the other way. The C naught has an analogous thing that's a sum gate. So A, B goes to A plus B, mod D. It's also in the Clifford group. The thing that really changes is this. So there's a totally different gate that kind of takes its place, which is a quadratic phase gate. And that's deeply tied into this difference about qubits versus QDITs, with the i's appearing in the Pauli group. And then there's also other stuff like scalar multiplication, which is just meaningless for qubits. So if you take the basis state x, you can take it to cx, the basis state cx. Yeah. So this is, again, a Clifford group operation for fixed C. And for qubits, it gets C can only be 0 and 1. But for qtrits, it could be 2 and so on. You could get a value. So basically, it works the same way. And all these other properties hold too, at least for prime dimensions. Any other questions?